And hi, welcome. So without further ado, let's start. In the last video, we talked about Newton's law of cooling, and I was saying, it is kind of a problem for us to have our quantities not dimensioned. What do I mean? Our mass right here, if we hover over it, and of course we use Rust Analyzer as we were talking about the last time, you'll notice that this mass is of type F64. It's a 64-bit float, otherwise known as a double. It just means it's a number with decimal places. However, there's no unit attached to this number. So it is very easy to make uh, a lot of these unit mistakes, right? Unit mistakes. So you could be adding mass to let's say the heat capacity CP, and you won't even know what you're doing wrong. Okay, so I just want to introduce this library which I love to use called Units of Measure, otherwise known as UOM, created by this guy called I Like Turtles, Mike Boutin, I think. Yeah, he's owns this repository. I just like him for the memes because I Like Turtles used to be a meme. I digress. Okay, so anyway, this is a very, very good library to use for units. It's licensed under Apache or MIT. It's dual license, so use whichever you want. Use whichever you want. Both of them are open source licenses with slightly different terms and conditions, but otherwise, pretty much you can just use it as is. Okay, remember we already talked about how to add crates, so that I won't say too much. Just use cargo add UOM and you will add the UOM crate. You'll notice that things like auto convert F32, F64, so on and so forth are okay. Do note that this crate also has support for complex numbers and integers as well. But and of course Serde and try from, so on and so forth. But you do not really need to have all of these in the crate. Just use the standard crate. You will get most, if not all, of the what do you call that? You will get most, if not all, of the benefits already from it. So what I'm going to do is I'm just going to do my cargo watch -x run as usual. Okay, and what you'll do is that we'll compile everything such as UOM, type num, so on and so forth. Then what I want to do is change this whole code to start using these units of measure. Okay, so it's gonna take a while to compile. Let it do its thing. Oh, it's already compiled. Okay, again, I forgot to actually ignore my CSV files. That's why it's doing this strange behavior. Okay, so you just have x equals to 2.5. You have all the old outputs from last time. So let's change all of this to use these units of measure. Now, first line, of course, is mass. Okay, first line is mass. How do you actually make a mass quantity? Now, first, you need to use you need to start using UOM first. So you use the keyword as such. Use UOM : SI : usually it's F64 or so on. You can actually scroll through here. You will be able to see lots of things you can put. Okay, usually I put F64 and then I put the star sign. This star sign again is a as I mentioned before, this is a wildcard. So you have adding this line here, use UOM SI F64 star with all the colons in between them. That will enable you to use the UOM package. Save it up, and you'll only see a warning here called unused imports because you're not using anything within here yet. So let's change this mass to be something more of a unit. So just bear with me, the syntax can be a bit lengthy, but yeah, you will see its use shortly. So this is a 2 kilogram thing, right? or rather, let's just assume it's 2 kilogram. Okay, the way to specify that it's 2 kg is this mass. Okay, use the new command. Yeah, if you're not sure, just type mass with a capital M, and you can actually put colon, and Rust Analyzer will actually give you lots of options for autofill. Okay, to make a new mass quantity, use the new method or the new function. You'll see this new with some inputs you can put this in. So this is the function, and you'll see that instantly this actually changes to a quantity type. Okay, so it is a new function, but you need to supply the units. So what you do is do colon again, and I'll put kilogram here. Okay, and then we'll have 2.0 over here. Yeah, I'll put the 2.0 thing over here. And this is how you specify that it's a new kilogram. If you're not sure, do go online and check. Okay, so now you see actually there's an error because there are a number of things. First of all, kilogram is not you cannot find the type kilogram. So just right click, and there's supposed to be a little bit of code actions. Okay, I know how to do this in OpenFOAM, but let me check how to do it here. Okay, maybe refactor. No refactoring. So okay, let me pause the recording. Okay, so hover over it. You'll see two things here. Rust Analyzer will give you a few options. One is to call view problem. The other is called quick fix. So the one I want to use is a quick fix. So click the quick fix option, and then it will say, okay, you can import UOM as mass kilogram or qualify as UOM as mass kilogram. So just do the quick fix. Again, right click and go to quick fix, or you can just type control dot. Okay, that's the quick fix. Okay, this is the thing I love about Rust Analyzer. It gives you a lot of options like this. Now there's another way to do it in Vim, but I'm not going to discuss it here. Just import this and save. Okay, you will at least have kilogram now imported in this scope. Okay, and now what's the problem now? Now I can see this thing here. It says let denominator equals to denom term 1 plus denom term 2. All right. So what's going on? Denominator term 2. Where's denominator term 2? Okay, denom term 2 here is a F64. Denom term 1 is what? It's a quantity. Okay. So you see this quantity denominator term 1 is no longer a float as it was before. It is now a quantity based on the units of measure package. So denominator term 1 is actually mass times CP. CP is still F64. Times that is still F64. So what this is saying is that, well, if you multiply quantity by a float or divide it by a float, you will still get the same quantity. So this denom term 2 is now in a so-called mass. If you want to actually take a look more, you see this L here. If you take a look at this dimension, this L here is length, M here is mass. So this mass is a positive integer, int u term b1. Okay, so it's a little bit complicated to read, but what this is saying is that the mass dimension is to the power of 1. Everything else, like temperature, current, thermodynamic temperature, and all the other things which I can't really, I'm not too sure off the top of my head, but those things are to the power of 0. So what this is saying is that this is a mass quantity. Okay, by and large, I don't really read this from time to time, but what I'm saying here is that this mass, this is obviously a mass quantity, and this denom term 1 is now of the type mass. It's a mass quantity unit. So the thing is that you cannot add a mass quantity unit to a float 64. You'll have compiler errors like this. So basically, the nice thing about the units of measure is that it will make the compiler tell you, hey, you're doing something wrong. You're adding the wrong units together, or things like that. So the only way you can add a mass to another number is if that same number is a mass. So look at this denom term 2 is a F64. Okay, the only way that this thing is going to work is that if if you multiply denom term 2 by a mass, so that denom term 2 becomes a mass unit as well. Okay, if you do this, of course it will run. Okay, and then you will find that most of the other things here, like this numerator term 1 and numerator term 2, now the problem sort of goes there. Okay, so what I'm trying to say is that this package prevents you from adding the units of the wrong type together, or yeah, unit-based errors like that. Okay, so what you need to do now is just to actually convert all these types to their respective quantities. So let me just quickly do that. So for example, this one is heat capacity, right? So I need to add is a specific heat. So there's a specific heat capacity. Okay, do new, and then again colon joule per kilogram. Okay, if you're not sure, you have to look it up online, but I use this a lot, so I know what units there are. You'll have to look it up online. Okay, so again, joule per kilogram Kelvin is not given to us, so you can just import it as so. Okay, and this CP now is of the proper dimensions. So let me show you where you can find all these quantity units. Otherwise, it's very hard. Otherwise, you'll be looking at the rest of the video not knowing what to do. So let me just bring you there. Okay, UOM cargo Rust. This is what I searched on Google. Go to the Rust crate registry. All right, and go to the crate registry. I'm going to minimize VS Code. And what you need to do is go to the docs. This is the documentation, docs.rs. All right. So what you can see, this is one place you can actually see what all the units are. Look at this: SI, absment, acceleration, action, so on and so forth. There are lots of units. Look for the one that is actually specific heat capacity. Specific heat. So just search that, or rather specific heat. Yeah, see specific heat capacity. Okay, this is where you can find that. So this is one place you can look. There's a lot of things here. In fact, a bit too many things to look. But for example, you look at this: SI area, square attometer, square centimeter. All of these are actually units of area. Okay, so if you actually look for specific heat capacity, okay, I mean there are two things you can look for: specific heat capacity with capitals like this, and this is what we call camel case, because the first letters of every single new word is capitalized, so it looks like the humps of the camel. So we call this camel case, or we can use snake case, specific heat capacity with. So snake case is that with underscores in between. So specific heat capacity like that is called snake case, whereas specific heat capacity like this is called camel case. All right. So look for either snake case or camel case, and that'll help you to filter some of the results. Okay. So look at UOMSI specific heat capacity. Open this up, and then you will see all the units you can do here. You can use here. So joule per gram per degree Celsius, joule per kilogram Kelvin, joule per kilogram degree Celsius, so on and so forth. You can find pretty much almost all the units you need to use here. Again, if that is intimidating for you, you can go to the GitHub repository for UOM, go to source, okay, go to SI. And of course, this works for today. It may not always work in future, because in future we may have updates to the crate and some of the information may be outdated, but for today this is how you do it. Okay, go to a specific heat capacity, and you look at all of these Rust files. These are all in snake case. Remember, snake case is that with the underscore, because that looks like a slithering snake or something like that. Yeah, so snake case. Okay, so go to specific heat capacity. So S is here. Go to specific heat capacity.rs, and you will see the appropriate units. You can remember just now there was 7 units here. Length, mass, time, electric current, thermodynamic temperature, amount of substance. That's why you get moles, and then luminous intensity. Okay, go down here and you will see all the units you can use. Joule per kilogram Kelvin, square centimeter, second Kelvin, something like that. Yeah, I don't want to read all of this. This is just some of all those units you can use for specific heat capacity. Right. So have a look. Go around and take a look in UOM source. You will be able to find some of the units you can use here. Okay. Or else you can just use the quick fix thing and hopefully something will show up. Yeah. All right. Heat transfer coefficient. What's the units of heat transfer coefficient? It's a H. Okay. Let me think. Okay. This one is called heat transfer. Okay. Oh, even autocomplete is already doing it for you. Heat transfer. So this is the quantity you need to use. New I think it's heat flux watts per meter squared Kelvin. Something like that. Okay, something like that. So I'm gonna go all the way to the end and do things like that. Okay, I might get it wrong. Let's see what the suggestions are. You might be missing a type parameter. Let's see if there's a quick fix. Okay, look for no quick fixes available. Okay, so again, if you're not sure, I can't remember off the top of my head what the units are. So let's go look for heat capacity. Oh no, heat transfer. That's the word. Look for heat transfer. Heat transfer is here. So click on it and open. You will see some of the units here. Kilogram per second cubed. Let's look for something with joules. I'm going to use a search function. Joule or watt. Okay, watt per square meter Kelvin. Okay, look for the one with watt. Okay, so the watts are all here. Watt per square meter Kelvin. Yeah, that's the word. Okay, look, let's type that in word for word. In exact case, watt per square meter. Oh, square meter, not meter square. Okay, so yeah, this is why you kind of need to go and refer to the repository every now and then. Square meter. Okay, square meter. And let's see. I'm gonna right click. Or hover over it. Hopefully there's a quick fix. Yes, there's a quick fix. Let's import it in. And here you have imported the unit. Now I understand it might take some time to get used to this system, but the long-term results are really worth it. So trust me on this. Yeah. Okay, so area is as such. Area, again, area, colon, new, colon, square meter. Or maybe centimeter or square centimeter. Square centimeter. Okay, 5.0. Finish this up. Again, this one is you'll need a quick fix. So just quick fix it with importing. Okay, so yeah, use Rust analyzer. It's really, really helpful. Okay, temperature of the surrounding, we'll put in thermodynamic temperature. Okay, new. Okay, degree Celsius. Okay, so I'm doing this because I already kind of know most of the units. But again, let's do a quick fix here. Import degree Celsius. Okay, so for degree Celsius, there are two kinds of degree Celsius you can put. One is called temperature interval, and one is a thermodynamic temperature. Okay, for now, just do thermodynamic temperature first. I'll tell you what the difference is. Yeah, right now. Okay, but since the surrounding temperature is a temperature in itself, it's not an interval. Okay, so we'll just call it a thermodynamic temperature. Now, why is there this need for difference? So uh, let me just explain. Okay, so we know that 0 degrees C, 0 degrees C, that's the freezing point of water, right? 0 degrees C is actually about 273.115, yeah, 15 Kelvin, 273.15 Kelvin, right? So that's thermodynamic temperature. 0 degrees C is 273.15 Kelvin. However, if you talk about the interval between 0 degrees C and 1 degree C, okay, you talk about the interval between 0 and 1 degree C, the temperature interval there is 1 degree C, right? Is 1 degree C. So 1 degree C minus 0 degree C is 1 degree C. However, the 1 degree C there, 1 degree C there is a temperature interval, because the intervals between 0 degree C and 1 degree C is 1 degree C or 1 Kelvin. In this case, when you talk about temperature intervals, both Kelvin and degree Celsius, they are equivalent. Okay, so you need to sort of differentiate between temperature intervals where Kelvin and degree Celsius are the same, versus if you're measuring an absolute temperature, which is called thermodynamic temperature. Okay, in this case, 0 degrees C is 273 Kelvin. It is not 0 Kelvin. Yeah, in the case of thermodynamic temperature. But when you're talking about intervals, the 0 degree C interval is a 0 Kelvin interval. Okay, so that's why there's a need to sort of differentiate them. Okay, so now let's do for the time step. Okay, so time, new, second. Okay, most of the time you can do some guesswork, especially for SI units. Their spellings are quite standard. It can be second, minute, so on and so forth. Control dot for quick fix, import a second. Again, there are two kind of second you can import. There's a UOM-SI angle second and a UOM-SI time second. So you will want to import the unit for time rather than angle, right? So somehow angles can be measured in seconds as well. I don't use those, so I'm not too familiar, but that is that. Okay, so temp solid initial, this is of a type F64. So this actually needs to be another thermodynamic temperature. Thermodynamic temperature new, this is degree Celsius. Okay, degree Celsius 400. So this is 400 degrees C. So now basically every of your units, these are now converted into quantities. Okay, of course you'll see that these things here are a little bit cumbersome. They are sort of in the way. You can of course switch this off if you want. Yeah, but yeah, you can switch it off if you want. Let me check how it's done, because I don't use VS Code a lot. So okay, so answer again comes from Stack Overflow. Okay, go to the settings page and look for Rust Analyzer inlay. So just credit to whoever answered kindly. So who is it? Yeah, Mindswipe. Okay, Mindswipe. Thanks to Mindswipe, we have the answer. So let's go to the settings and then change the Rust Analyzer inlay settings. Rust Analyzer. Okay, look for Rust Analyzer inlay. Oops, inlay. Okay, so for now the inlay hints are enabled. Okay, you can switch off some of these hints. Okay, switch off whether to show inlay type hints for method chains. You can switch off some of these hints. Render colon. Okay, type hints. Okay, I can switch this off. I can switch this off as well. Okay, I think this is the type hints. Yeah, I'm gonna switch off the type hints, and that will get rid of all the hints over here. So these type hints are a little bit too much. So I didn't want to have them. If not, it will be very, very cumbersome. But this is how it looks like without the type hints. Okay. So current time step, okay, I also want this to be a time new second 0.0. All right. Time step. Okay, so we'll see ourselves straight away having a few problems. For example, the string to string method doesn't work. Okay, so what you need to do, right? What you need to do, if you want to print these values out, okay, there are a few ways. First of all is to just use the value attribute within the current time step. That would actually make it work. However, this actually just extracts the value as a SI unit. Okay, so anything you will take out of these quantities, usually, see, you look at this is an SI unit. The module is SI. So all the values you actually take out, these are stored in SI units. However, the way I sort of prefer to make things a little bit more explicit is to use the get method. The get method needs a unit as well. So what the get method does is that it will, as long as you put in the unit, it will return the value in a float64 format. Okay, in this case, it's a float64 format because we use the float64 package here. See, float64, the mod float64. Okay, so what we do here is to get it in second. Okay, open and close braces. This will actually return a float64, and then you can use the toString method. Okay, I'm going to do the same thing here. Get degree Celsius. Okay, open and close toString. Okay, this will solve the toString problem because now you once you use the get method right here, we this time use a dot. Okay, use a dot, the get method, and then you put a colon with second. You will be able to convert it to the unit back to a float64. Of course, the learning curve is a little bit steep, but yeah, bear with me for a little bit more, and then we can move on. Okay. Now let's take a look at this. What is going on here? It says expected trade temperature kind found trade kind. So what is this here? Solid temperature at the next time step. Okay, solid temperature at the next time step. Okay, this is solid temperature at the next time step. What is the unit? Okay, so the units are the same. If you take a look, TH here is P int, so on and so forth. And if you actually take a look here, the units are the same. Okay, L is 0, M is 0, T is 0, I is 0, T is time here, and TH is temperature. I is 0, TH is again P int, U int, term blah 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 P1. However, the kind here is a temperature kind, whereas the kind here is kind. So what is this trying to say? Okay, again, I mentioned before, like just now, there's a temperature interval, right? There's a temperature interval and a thermodynamic temperature. Okay, so why is there a temperature interval here? Why is there a temperature interval here? If you take a look here, there's a surrounding temperature, temperature of surrounding thing here. Okay, there's a temperature of surrounding thing here. Here's the temperature of the surrounding, and you sort of add it to a solid temperature time step in the current time step. Okay, once you sort of add this numerator term 1 and numerator term 2 together, you sort of get rid of the how call this? Yeah, once you add these two numerator terms here, what UON will do behind the scenes is to convert those thermodynamic temperatures into temperature intervals. So there's some wizardry that goes on behind the scenes, okay? But the thing you need to do here is just to convert this type solid temperature time step or the solid temperature next time step into the correct kind of temperature. So let's see. So you see, solid temperature current time step is temp solid initial. So this is definitely a thermodynamic temperature. So we can actually do this here, thermodynamic temperature. And the solid temperature, the next time step, I need it to be a thermodynamic temperature. So this thing here actually just creates a binding for the variable, but it does not set the unit. Meaning to say, I'm just declaring that the solid temperature, the next time step, this variable exists, but I haven't set the value yet. Okay. I usually do this so that I can actually make sure the type is set. So this solid temperature at the next time step, we didn't specify the type, but I want to make sure that this is a thermodynamic temperature. So if you didn't understand what I said just now, maybe I'm moving too fast. Okay, the thing is that, yes, I want to make sure the solid temperature at the next time step is a thermodynamic temperature, not a temperature interval. So what I can do is I can specify the type explicitly like so to make sure that this type is a thermodynamic temperature. Okay, so solid temperature, the next time step, this is a thermodynamic temperature. All right, so this solid temperature, the next time step is a, yeah, I think the units are right now. Now you have this numerator divide by the denominator problem. Again, what's happening here? Again, what's happening here? You have a mass, you have a CP and a time step, heat transfer coefficient and surface area. So all of these here, they don't really contain a temperature, okay, except for CP and heat transfer coefficient. Okay, the unit here is the kind here is of dying kind. So what's going on here? All right, when you use temperature in CP, okay, I'm guesstimating, right? But I'm just trying to explain. CP is in joules per kilogram per Kelvin. Okay, what you care about in a specific heat capacity, those are actually temperature intervals. You don't really care about the absolute thermodynamic temperature. Same goes for the heat transfer coefficient, H. You usually care about the temperature intervals rather than the thermodynamic temperature. Okay, so these kinds, the temperatures housed within the CP and the heat transfer coefficient, these are actually thermodynamic temperature. However, once you have temperature of surrounding and the solid temperature at the current time step, now that these are actually added in, this actually becomes a temperature, the absolute temperature. So what UOM is trying to tell you is that when you add, let's say 25 degrees C plus 400 degrees C, how are you supposed to add them? Right, because there are two ways available. What let me just type that out. Okay, how to add 25 degrees C to 400 degrees C, right? Or how do you subtract them, right? I mean, you can do this intuitively, but let me show you why it's important to specify. Okay, when you have 25 degrees C plus 400 degrees C, okay, your knee-jerk reaction, your so-called instinct is just to have 425, right? You don't really care about the kelvins and stuff. But the thing is that once you add the kelvins to it, 25 plus 273, okay, so 25 degrees C is actually 293 Kelvin, just like what I explained earlier. Okay, and then 400 degrees C is actually 400 plus 273 Kelvin as well, so 673 degrees C. Are you going to add the 273 degrees Kelvin or C twice? Okay, and does it give you the same answer? So if you really add it like that, you have 425 plus 273. Okay, plus 273. So this is how many kelvins there are. Okay, is this method of addition correct? Well, not necessarily. So what you have to do now is to convert both of these, the temperature surrounding and the solid temperature, the current time step, you need to convert them to temperature interval. Okay, you need to convert them to the temperature interval, and then you will get the correct thing. Now, this is one advantage of having UOM around. it's there to tell you, hey, you got to specify nitty-gritty things like this. If not, your whole calculation can be wrong. Okay, so I'm going to explicitly so-called explicitly get temperature intervals here. Okay, let temp surrounding interval. Okay, and maybe let me just double check my equations. Oh man, I'm going really long. Okay, so I'll stop for now. Okay, should I stop for now? No, I'm going to continue. I'm going to continue and finish this up. Okay, I just want to make sure that things are correct units. So I'm going to bring out my calculation pad again. Okay, so this is it. Okay, see, right here. We bring the terminal down. Bring the terminal all the way down. So yeah, when we did the explicit Euler method, how did we get the equation here? Okay, we had the T solid at the next time step minus T solid right here equals to, yeah, plus this HA T solid, T minus T solid. And then now you have the surroundings as well. All right. So what I did is to bring this T solid right to the right hand side. Okay. So we can actually see these temperatures actually come as a pair. They come as a what do you call that? They come as a pair because these two temperatures, these are intervals. This T solid at the next time step minus T solid at the current time step, this is actually an interval. And likewise over here, this here also is an interval. The T solid at the current time step minus T surroundings. Okay, oh, sorry, this is the explicit, if I'm not wrong, explicit Euler method. Right, I'm doing the implicit one here. So T solid at the next time step minus T surroundings. These two they're actually temperature intervals. So they come as a pair. So these two come as a pair and these two come as a pair. So how do you make sure that this T solid here and this T solid here, they will actually get the so-called right. They will actually be the right thing. Okay, so my take is to actually say, okay, if T solid, this is in a Kelvin unit. So maybe this is what 473 Kelvin. This one's a 473 Kelvin, for example. And then these two are also in Kelvin. T solid in the last time step and T surrounding in the last time step. If these two are also Kelvin units, then you should not have a problem. Okay, so what you do is that you bring this T solid to the right hand side and this T solid to the left hand side, and you just make sure every single thing is in a Kelvin unit. So then the 273s will sort of cancel each other out. So that's how I sort of think about it. Yeah. Or rather, okay, if you don't want to deal with the 273 at all, convert all of this. Just take this all as a degree Celsius value, and that will be also a way to play safe. So if you scroll down here, if you scroll down all the way here, you have this thing here. You have the T surrounding at the last time step and T solid at the last time step. Okay, both of these should be in degrees Celsius, and this should be in degrees Celsius. So as long, the only thing is that you need to keep both of these all in the same units, and then the 273 Kelvin difference will sort of cancel each other out. So if you want this T solid to be in Kelvin, this T surroundings better be in Kelvin, and this T surrounding also, this T solid at the last time step also better be in Kelvin. If you want it to be in degree C, then all of them have to be in degree C. Okay, so that's how you just want to be careful with your temperature intervals there. Okay, so what do I do now? What's the application? I'm going to close this and close this. Okay, so CP, these are all in temperature intervals. Okay, but the solid temperature at the current time step, I want to get the degrees Celsius. So where's the denominator or numerator? Sorry. Okay, numerator is here. Okay, I'm going to change this value here to a temperature interval. Let temp surrounding interval, okay, degrees C. Okay, so I just want to be careful here. I'll have a temperature interval new degrees Celsius, and then I will have the temperature surrounding get degree Celsius. Now I cannot use the same degree Celsius here. Okay, I cannot use the same degree Celsius here because again the unit for temperature interval degree Celsius is different from the unit for temperature thermodynamic temperature degree Celsius. So you got to be very careful about that. Okay, so this one I need to change. Let's see whether there's a quick fix around. No quick fixes available. So okay, I'll just tell you the fix. Okay, UOM SI temperature interval degree Celsius. This will fix the problem. Okay, this you have to specify that it's a degree Celsius. So this is a lot of code here. So let me explain what's going on. I'm making a new temperature interval unit. So temperature interval new. I specify that it's a degree Celsius. Okay, remember just now I was saying a degree Celsius in temperature interval is very different from a degree Celsius when it's a thermodynamic temperature. Okay, so this is the interval version of the degree Celsius. So this is why there's a difference. Okay, so what is this? What is this here? I'm getting the float, the decimal value, the decimal number value of the surrounding temperature. So that the surrounding temperature happens to be 25 degrees Celsius. Okay, this function will just evaluate to 25. So it's as good as me putting the 25 right here. Okay. However, I'm actually putting the function like that here. So sometimes you will see people write code like that where they nest a function inside another function. Well, the way to think about it is to evaluate the inner function right here first. So I'm getting the value of the surrounding temperature in degrees Celsius. If you're not sure, you can hover over the get. You'll see that it actually gets the value. So V is actually a value type. Okay, you can't really tell that from here, but yeah, V is actually a value type. Okay, let me see whether okay, it's not giving you the full thing. So maybe you want to right click, go to definition. Okay, let's see whether we can find get. Okay, the get method is not showing there. Yeah, probably because there's a use of macros, but anyway, it will take very long if I were to explain everything and go through source code, but I won't do it. Okay, so just trust me on this. And then okay, let temperature surrounding degrees C float. Okay, so if it makes it easier for you, I'm going to do this so that the code doesn't look so intimidating. So remember, this is actually a float. As you can see, this is the float of F64. I'm putting the float in here. But what I was doing just now was a shortcut where I can just copy and paste this whole function and put it here so that the code is more concise. So I'm going to show you, I'm going to put it that way so that you have two examples. They are actually doing the same thing. So let solid temperature current time step interval degrees C. Okay, it's temperature interval new UOM SI temperature interval degrees C. And then I'm going to do this, right? I'm going to squeeze the whole thing in there, the whole expression in there. So what I want to get, what I want to do is the solid temperature at the current time step. Okay, and then I will use the get method with degrees Celsius. Okay, so these are two ways you can basically write the same kind of code. Okay, the surrounding degrees C. Okay, you bind this, we bind this, we make a new variable, we bind this temperature surrounding get degrees Celsius, we bind it to this value, and then we make a new temperature interval unit. The second method is to just, instead of having these two lines of code, we can compress it into one line of code. So solid temperature time step, we get the degrees Celsius. This will get the float value out. So the solid temperature of the current time step, we get it in degrees Celsius, and then we convert it into a temperature interval manually. Okay, once we do that, we can change the things here. So I'm going to change this because this is a thermodynamic temperature, but I want to change it to a temperature interval type. Okay, temperature interval. Temperature surrounding interval. I'm going to change this also to a solid current time step interval degrees C. Okay, solid temp current time step interval degrees C. Okay, I spelled temp wrongly. The autofill wasn't that helpful, but here's supposed to go. Okay, so I've explicitly stated that these two are temperature interval, but now this problem is that this solid time step is a thermodynamic temperature. That's why it's got the temperature kind here. Okay, I think I may have made a mistake earlier in the video. Okay, so when it says temperature kind, this temperature kind refers to absolute thermodynamic temperature. So I cannot just have this numerator and denominator here because this is a temperature interval type. Right, this is a temperature interval type. So what I need to do is that, hey, these two, this numerator and denominator, it's of a certain value, right? This is a temperature interval in degrees C. So I want to get my degree C value back. So remember, if we use degrees Celsius then we better make sure that this thing here is also a degree Celsius. So what I'm going to do is I'm going to use this shortcut method where I actually get the degree Celsius first from the temperature interval. Temperature interval degree Celsius. Okay, this is a floating value. Right? You see that this is a floating point value. So this thing here is a temperature interval, and then I'm getting the temperature interval in degrees Celsius. So this becomes a float 64. So once I have the float 64, okay, this whole number here is actually my temperature in degrees Celsius, but it's in just a number format. So I want to convert it into a thermodynamic temperature in degrees Celsius. So thermodynamic temperature, new degrees Celsius. This will make the new unit of thermodynamic temperature, and let's save it up. Now this thing will work, and let's actually check the output. Okay. Now understand this thing takes a while to get used to, so maybe I will do a few more simple examples that hopefully will help. Okay, maybe I'll do something like an ideal gas or something. It's a little bit easier, and I'll do it a bit slower. Okay, so we'll go through another example again, so so that we can deal with it a little better, because it's a bit of a steep learning curve. Totally understand. Okay, so I'm going to open the Newton's law thing, and hopefully it gives me the right answer. Okay, so I do have the temperature going from 399 all the way down. In fact, it is going down, but it's going down really slowly. So time and temperature, degrees C. Okay, so the simulation works is the temperature is actually going down really slowly, but it's a bit too slow. Doesn't really make sense. Oops, I should have given you a let's give you a chart, scatter plot, and finish up. Yeah. So yeah, we do see a decreasing temperature, but probably the thermal inertia is so much that the temperature doesn't change a lot. So what I'm gonna do is well, let me reduce the mass of the thing. Let me reduce the mass of the object. So instead of having a 2 kilogram object as you see here, let me see. Yeah, this mass is a 2 kg object, so it's a huge thermal inertia. Why not let's change this to gram? I'm going to change this to gram, and let's see whether there's a quick fix. UOMSI mass gram. So this is just an example to change the unit. And what happens is that, okay, this temperature should go down a lot faster. I'm not going to save this. I'm going to have my Newton's law of cooling CSV file from here, and I'll put it here. I'll overwrite it, and voila. Okay, temperature is going down a lot faster because there is less thermal inertia. Let's go on top. Time, second. Temperature, degrees C. Okay. So let's insert a chart. So you see, okay, so we reduce the amount of substance being cooled. And you can see the cooling curve actually does make sense. It's cooling a lot faster than it was in the previous simulation. Okay, so and what I did was just to change the unit, and we saw that instead of a 2 kilogram thing, we have a 2. Okay, yeah, instead of a 2 kilogram mass, we have a 2 gram mass. With a 2 gram mass, this thing actually cools down a lot faster. Okay, so that is the thing here. Now, of course, if we increase the area, we should expect more heat transfer as well, but I'll stop the example now, because I think this is a very long video. It's almost an hour, my goodness. Okay, yeah, it's a very long video, but I hope it's been useful in introducing you to UOM. If you still didn't get what's going on, I'm going to slow down, maybe going to introduce to you through another example, a unit UOM, because I think this example is a little bit too complicated for a first example. So I'll see you next time.